Hey there, fellow software engineers. Welcome to Section 2.2, where we'll dive into the fundamentals of supervised learning. As someone who has made the journey from software to machine learning myself, I know this can feel like uncharted territory at first. But don't worry, we're going to navigate this landscape together, one step at a time. Supervised learning is all about learning from labeled examples. It's like having a wise mentor guiding you, showing you the ropes. The algorithm learns from the input data and its corresponding correct outputs, and then uses that knowledge to make predictions on new, unseen data. Think of it like teaching a child to recognize animals. You show them pictures of cats and dogs, labeling each one. After seeing enough examples, they start to learn the distinguishing features. Cats have pointy ears, dogs have rounder snouts. Soon enough, they can confidently classify new animal pictures they haven't seen before. That's the essence of supervised learning. In this section, we're going to explore the two main types of supervised learning problems: regression and classification. We'll also touch on some specialized applications like time series forecasting and instance-based learning. So grab a cup of coffee, settle in, and let's start this learning journey together. Lesson 221: Regression Algorithms. All right, let's kick things off with regression. Imagine you're trying to predict the price of a house based on its size. You have data on house sizes and their corresponding prices. This is a perfect setup for regression. At its core, regression is about finding the relationship between input variables, like house size, and a continuous output variable, like price. The goal is to draw a line or curve that best fits the data points. This line is then used to make predictions for new input data. The simplest form of regression is linear regression. It tries to fit a straight line to the data. If you have just one input variable, like in our house example, it's called simple linear regression. But if you have multiple inputs, like size, number of bedrooms, location, etc., then it becomes multiple linear regression. But what if the relationship isn't linear? That's where techniques like polynomial regression come in. They can fit more complex, curved lines to the data. Now, how do we know if our regression model is any good? We use evaluation metrics. Some common ones are mean absolute error, mean squared error, and R-squared. They essentially measure how close the model's predictions are to the actual values. So that's regression in a nutshell. It's all about predicting continuous values by finding the best fit line or curve. Next up, let's talk about classification. Lesson 222: Classification Algorithms. Welcome back. In the last lesson, we saw how regression helps us predict continuous values. But what if we want to predict categories instead? That's where classification comes in. Think about spam email detection. Each email can be classified as either spam or not spam. This is a binary classification problem because there are only two possible categories. One of the fundamental algorithms for binary classification is logistic regression. Despite its name, it's actually used for classification, not regression. It works by fitting an S-shaped curve, called the sigmoid function, to the data, and then using this curve to predict the probability of a new data point belonging to a certain class. But sometimes, a linear boundary isn't enough to separate the classes effectively. That's where algorithms like decision trees and random forests shine. They can create complex decision boundaries by splitting the data based on different features. Support vector machines, or SVMs, take a different approach. They try to find the hyperplane, a line in higher dimensional space, that maximally separates the classes. SVMs can also use kernel tricks to transform the data, allowing for even more complex decision boundaries. And let's not forget about naive Bayes. It's based on Bayes' theorem from probability theory. Despite its simplicity, it can be surprisingly effective, especially for text classification problems. To evaluate classification models, we use metrics like accuracy, precision, recall, and F1 score. They give us a sense of how well the model is predicting the correct classes. So there you have it, a whirlwind tour of some key classification algorithms. Each has its strengths and weaknesses, and the best choice depends on your specific problem and data. Lesson 223 Time Series and Forecasting. All right, let's change gears a bit and talk about time. Specifically, time series data and forecasting. Time series data is a sequence of data points indexed in time order. It's everywhere: stock prices, weather patterns, sensor data from IoT devices, you name it. The key thing about time series is that the order of the observations matters. Forecasting is all about predicting future values based on past observations. It's like having a crystal ball, but instead of magic, we use math and data. One of the classical approaches to time series forecasting is ARIMA, which stands for Autoregressive Integrated Moving Average. It's a bit of a mouthful, but the key idea is that it uses the past values of the series to predict future values. ARIMA can handle trends, seasonality, and other complex patterns in the data. But machine learning has also made big strides in forecasting. Techniques like recurrent neural networks, RNNs, and long short-term memory, LSTM, networks can learn intricate patterns and dependencies in the data. The key challenge with time series is that the future is uncertain. Unlike regular supervised learning, where we have the true labels for our predictions, in forecasting, we have to wait for the future to unfold to see if our predictions were right. This makes evaluation trickier, but techniques like rolling origin evaluation can help. So next time you see a weather forecast or a stock market prediction, you'll know there's some serious time series modeling going on behind the scenes. Lesson 224. Instance-based learning. Last but not least, let's talk about instance-based learning. This is a family of algorithms that don't really build a model. Instead, they memorize the training data and use it directly to make predictions. It's like learning by memorizing examples rather than extracting general rules. The poster child of instance-based learning is the k-nearest neighbors algorithm, or KNN. The idea is simple. When you get a new data point, look at the k closest points in your training data. For classification, take a majority vote among these neighbors. For regression, take the average of their values. That's your prediction. But how do we define closest? That's where the notion of distance or similarity comes in. Common choices are Euclidean distance for continuous features and Hamming distance for categorical ones. The choice of distance metric and the value of k can greatly affect the results. One advantage of instance-based methods is that they naturally handle multi-class problems. They can also adapt quickly to new data, just add the new instances to the memory. But the flip side is that prediction can be slow for large datasets, since you have to search through all the data for each prediction. This brings us to an important distinction: lazy versus eager learning. Lazy learners like KNN wait until prediction time to do the heavy lifting. Eager learners, like decision trees, build the model up front during training. It's a trade-off between training and prediction time. So that's the essence of instance-based learning. It's a simple yet powerful paradigm that's worth having in your machine learning toolbox. Recap and conclusion. Well, folks, that was quite a journey. Let's recap what we've learned. We started with regression, learning how to predict continuous values by fitting lines and curves to data. We saw how linear regression, both simple and multiple, can model straightforward relationships. And we learned about polynomial regression for more complex nonlinear patterns. Next, we dove into classification, the art of predicting categories. We saw how logistic regression can draw a line between two classes. We explored decision trees and random forests that can create intricate decision boundaries. We marveled at the elegance of SVMs and the simplicity of naive bays. Then we took a journey through time with time series and forecasting. We learned about the unique challenges of time-ordered data and how techniques like ARIMA and machine learning can peer into the future. Finally, we explored instance-based learning, where the model is the data itself. We saw how KNN can make predictions by looking at the nearest neighbors, and we pondered the trade-offs of lazy and eager learning. Through all of this, I hope you've gained not just an understanding of these algorithms, but also an appreciation for the diverse and fascinating world of supervised learning. Remember, machine learning is a journey, not a destination. Keep exploring, keep questioning, and most importantly, keep learning. The best way to solidify these concepts is to get your hands dirty with some real data. Try implementing these algorithms, play with different parameters, and see how they behave. And always remember, whether you're predicting house prices, classifying emails, forecasting sales, or recognizing handwritten digits, supervised learning is your trusty guide, helping you navigate the complex landscapes of data. So go forth and conquer, my fellow data adventurers. Until next time, happy learning.